In this problem, we have a wooden block sliding down an inclined plane with a constant velocity of 14 meters per second. That's going to be key to this problem, constant velocity. How large is the coefficient of kinetic friction if the plane makes an angle of 31 degrees? So let's draw ourselves a free body diagram here. Doesn't matter which way we let this incline slope. We have a 31-degree angle. This block sliding down the ramp. So we have a velocity going down the ramp. But we have a constant velocity. So I know the acceleration must equal 0. And if the acceleration equals 0, then the net force will likewise equal 0. Well, what forces do affect this block here? Well, we're going to have a force of gravity that's going to point straight down towards the center of the earth. We're going to have a normal force. That normal force must be perpendicular to the surface of the ramp. If we're sliding down the ramp, then we're going to have kinetic friction pointed back up the hill. Always friction's opposing our motion. And so as we start to look at this, we want to look at what are the forces on the x-axis. Well, again, we have 0 acceleration and 0 net force. That's going to be true on the x-axis and the y-axis. So on the x-axis, well, what's bringing us downhill in the first place is that part of this gravity is going to make us slide down the hill. This gravity has an x component. And if we're trying to find this x component of gravity, I'm going to draw this just a little bit larger down here. In fact, let me draw it a little bit larger on a clean sheet of paper. So if we have this block on our incline, a 31-degree incline, force of gravity going straight down here. Well, this gravity is going to have an x component. We'll call that mgx. And it's going to have a y component, mgy. What is true is that this angle right down here, okay, this 31-degree angle, sorry, I don't know why I wrote 30 there. This 31-degree angle is going to be the same as this angle right here. If we look at this large triangle as well as this smaller triangle, they're similar triangles. They're going to have equal angles. Now, let me move and say that this x component right here and make this into a triangle. This x component's really going to look more like this. And let me extend this one on down. This is what I get for drawing things in real time. Okay? So if you've got the force of gravity going straight down, it has a y component that's perpendicular to the incline. It has an x component that's parallel to the incline. Well, the x component is now the opposite side. The y component is the adjacent side of this triangle. So that means if we know the weight of this object or the force of gravity, then we want to get the x component. It is the opposite side. So the x component must equal this vector, the force of gravity, times the sine of our angle, because sine of theta itself is the opposite side, mgx, divided by the hypotenuse, mg. And so what we've done here is just get mg, the x component, on a side by itself. Likewise, if we want to talk about the y component, well, this y component is the adjacent side. So the cosine of this angle would equal the adjacent y component divided by the hypotenuse. And so the y component is the force of gravity times the cosine of theta. And these are going to be important. We're going to install these in our equation in just a moment. All right, so using these, keep these in mind. We're going to use these on our formula here. That on the x-axis, we have that x component of the force of gravity going down here. We're going to say all the way, by the way, downhill, we're going to call that positive, call uphill the negative. I like to make the way I'm going the positive directions. I have a positive velocity. So that x component, it's all going to equal 0 because that's the net force. The x component, the force of gravity, times the sine of theta minus the kinetic friction. Those are the two forces, or the force and the component of the force, that are on the x-axis. All right. On the y-axis, the net force is also 0. We have the y component for the force of gravity. Okay, this y component we talked about right here. So we're going to say the normal forces are positive going upward, minus the y component, mg cosine theta. Those are going to equal 0. Well, in both of these, we can say that if they equal 0, these two forces must just balance each other out. I should have done that a moment ago when I was up here writing this part out. Okay? Now, the other thing is, because we have friction, this kinetic friction will always equal the coefficient of kinetic friction times the normal force. So what we've got here is several unknowns. We don't know the force of friction. We don't know the mass of this object. We don't know the normal force. But these equations now start to come together. That the kinetic friction is mg sine of theta. That the normal force is mg cosine of theta. And so as we bring this together, we're saying that mg sine of theta equals the coefficient times the normal force, mg cosine of theta. Now, when I get to this point, I've eliminated these variables. The normal force is no longer here. The force of friction is no longer here. And now we have mg on both sides of the equation. The mass is eliminated as well. And so we're left to say that sine of theta equals the coefficient of kinetic friction times the cosine of theta. And so if I divide both sides by cosine so that it cancels out, well, sine divided by cosine is the tangent. And so what we're left with is that the tangent of this angle equals the coefficient of kinetic friction. So the tangent of 31 degrees is the answer we're looking for. So tangent 31, my calculator's in degree mode. Tangent of 31 equals 0.60. It's our coefficient of kinetic friction.